Yes, perfect. So, in previous video, we saw that if we consider the spectrum and if we consider the Fn as 256, so basically, if we consider Fn by Fs ratio as 1 by 4, then we will somewhat get a graph or a plot of the coefficients like this, and this will mislead us by stating that our system is working perfectly fine and there are no harmonics. But actually, the harmonics are getting aliased back into the same bin. So we talked about this, and I would like to talk about the same, but I would like to derive it in the other way or other fashion. So let's take the Fn by Fs ratio, some value which is 259 by 1024. So the Fn by Fs comes out to be the value 252 times some decimal points. So basically what we are doing is, while actually characterizing our sample and hold, Fs is fixed, sampling frequency is actually fixed, and we need to choose Fn in such a way that it satisfies the desired condition for periodic discretized sample x of n. So basically we need to generate a sinusoid with such value where there are decimal points as well. So it's practically impossible to keep Fn and Fs to sync throughout the entire process, because we had to maintain the ratios, right? So we have our sampling frequency, so there is some clock for Fs, or let's say we have generated Fs and we have generated Fn, so we have to keep both of them together in a ratio, which ratio is uh, given by this value for this set of example. So practically it's impossible for keep it throughout the procedure. So we need to synchronize both Fin and Fs with respect to either a reference frequency or with respect to each other after every designed or estimated period. So we can also say it in a way that for 1024 uh, Fs cycles, we have 259 cycles for Fn. So we check it after every period. Let's say that period is constant and we have determined or estimated that period. So after every each and every period, we check that are there 259 cycles for Fn for 1024 cycles of Fs. And if the Fn cycles are lesser than 259 in 1024 cycles of Fs, then we increase the frequency of the oscillator for Fn, or vice versa. So basically, this is a negative feedback loop, and this loop is basically called as phase locked loop to keep Fin and Fs synchronized. So, and it is necessary to keep them synchronized because this ratio must be maintained. But again, what if Fin was slightly off from this required ratio or this value? So it goes up to decimals, right? So let's say Fin by Fs, let's take it as 129 by 1024. So we get a spike or increase in the magnitude for the coefficient at 129th win, right? So what if Fn by Fs was 129.001 instead of 129 itself? So it is like by our naked eyes, it's just a very small difference. So can we round it off to 129, or can we just neglect that zero point zero 0.01 decimals? So this is what I asked you to work out in the end of the previous video, said that work with the decimals and play around it. So basically, we will be talking about this kind of a effect. So when we a quick sentence I would give. So if we have a ratio which is not 129, but it is 129.01, then this is a plot for 129, and this is a plot for 129.01. And if it approaches to 129, so let's say for 129.001, the plot will be somewhat like this. and as it approaches to 129, it will go like this. But then all the bins are full. So actually we wanted just the 129th and 1024 minus 129th bin to be full. But now in this case, all the bins are full, and basically it's stating that our sample and hold is doing really bad job. So basically this graph is coming from the artifacts of fast Fourier transform, and we'll soon discuss it. I just wanted to give a quick statement on what happens when we neglect or we consider it as very small change. It's actually not. So basically, we have two questions in front of us. So why is this happening, and what can be done to fix this? So let's focus on why is this happening first. So because of 129 being shifted to 129.01, the Fn does not satisfy the condition anymore for x of n to be periodic. And when we compute its discrete Fourier series, all bins will be taken by the coefficients of DFT. So ideally when it was 129 sharp, so all the bins were empty and only the 129th or the mth bin was taken by the coefficient of discrete Fourier series. But now all the coefficients will take the bins, and that's how the plot will look like. So we'll discuss why is this actually happening. So basically, if we have a finite length of sequence and its length is, let's say, capital M, so its discrete Fourier transform is defined by x of j omega equals to this value. And when we take the discrete Fourier series of this DFT, which is denoted by x of k, then it comes out to be of this value, where we have x of n e to the power minus j omega 2 pi k by m times n, and this k goes so basically this m goes from 0 to m minus 1, because it's just the repetition of a particular sample from the DFT. So basically over here the discrete Fourier series is just a sample version of DFT of x of n, where we have picked just 0 to m part, and we have repeated it periodically. So the discrete Fourier series is a Fourier series representation of periodic extension of this m point sequence given by x of k. So we have from 0 to m samples, and they are repeating themselves after a period m. So we can look at it that way. So if we have a sinusoidal discrete signal, so let's say we have at the output x of n we had, right? So let's say we have that sinusoidal discrete signal, and let's say it is cos of a of n, where a is its frequency. So then cos of a of n, so this is all the way from minus infinity to infinity, and it goes like this. So basically the discrete Fourier transform of this signal will be pi times delta omega minus a plus delta omega plus a. And if we are only interested in the chunk of the system lasting from 0 to m samples, then in principle, this is equivalent to taking a cos an and multiplying it with a rectangle lasting from 0 to m minus 1. So basically m samples. So what I mean by this is, so basically we have cos of a of n, and we will multiply with the samples, a chunk of rectangular sample, which is going from 0 to m minus 1. So basically which are m samples. And the Fourier, so basically when we talk about this whole signal, so its discrete Fourier transform of this whole signal is nothing but the convolution of Fourier transform of cos of an and the Fourier transform of this signal. And what is the Fourier transform of this signal? So basically Fourier transform of m minus 1 m samples, basically from 0 to m minus 1, it is given by 1 plus e to the power minus j omega plus and so on e to the power minus j omega till m minus 1. So it is basically represented by this value, where this part has a magnitude of 1, and the average, like where did this m minus 1 by 2 came from? So basically it's representing the average delay of the samples 0 to m minus 1, and the average delay lies at its center. So that's why it's m minus 1 by 2. And this here is an even function of time. So which means it has a delay of 0. So when we talk about its magnitude, so basically it will give us a peak over here, and it is omega m by 2, right? So when we consider this whole signal, so basically the convolution of cos of a of n and this rectangular box is basically when we have a discrete Fourier transform of cos of an times the signal is nothing but omega n, where the length of n is m samples. So it is given by, so the magnitude of this function is given by the multiples of 2 pi by m, 4 pi by m, and 6 pi by m, and so on. So this is what the magnitude of this even function looks like with a delay 0. So the DFT of total function will have a spectrum where this point is nothing but a. So if we compute, so we have the DFT, discrete Fourier transform, of this complete signal, right? So now to if we compute the discrete Fourier series of this DFT, we will get a discrete Fourier sample, which is like, we know that the DFS is basically a sampled version of discrete Fourier transform. So which is basically sampled at 2 pi by m, right? So we have 2 pi by m, and a equals to k times 2 pi by m, where k is an integer. So we have 2 pi by m, 4 pi by m, 6 pi by m. So when a is basically 2 pi by m, so then our a becomes k times 2 pi by m, where k is an integer, and the Fourier series is again it's a sample version of DFT. So this is how the spectrum of discrete Fourier series looks like, and that's why these are the samples over here of our DFS, right? So uh, based on this spectrum, we can say that we see the peak at the mth bin for Fn by Fs equals to m by n, and all other bins are basically 0. So the thing is, what happens when a is not a multiple of 2 pi by m? So we are talking about the condition where we had this thing. Instead of 129, it is 129.01. So when we talk it about in time domain, so what happens when a is not a multiple of 2 pi by m? So this phenomena is called basically a leakage in FFT, where Fn is not residing to a particular bin. So what happens is, now the samples get shifted. So when they get shifted at these points, then they'll be not 0. So over here, the sample have 0 values, and it is a peak at this coefficient where it is a. So, and a is given by this thing. So due for the sake of having the discrete Fourier samples or series. So uh, if a is not a multiple of 2 pi by m, then the samples will be shifted. And if the samples will be shifted, then at each sample or each bin, we will have some sort of values. And that's why we will get such plot. So the plot will be like this, instead of just a peak at this point and other points are 0. So that's why when we see the plot, so we saw that we only have a peak at mth bin, where we have m as 256, and we don't have any other bin occupied with a coefficient. So let's take an example where we have Fin by Fs as 129 divided by 1024, and when we run this code, then we get 3 harmonics like this, right? And what if instead of 129, we take 129.01? So what happens is, so we will see the phenomena of uh, leakage in fast Fourier transform, where Fin will not reside to a particular bin. So this is what happens. Every coefficient, like every bin is now taken by the coefficients of discrete Fourier samples. And this is the center of symmetry, and everything over here is just a mirror image of this part. So if we go closer to 129, let's say we take 129.001, then this graph will reside more closer to this one. So if we go more closer, let's say this value, then it will reside more closer. And when we go sharp 129, then we have peaks just at those bins and all other bins are empty. So this is the phenomena of leakage in fast Fourier transform. So that's all for this video from my side. Thank you so much. So if you have doubts, let me know.